So, hello everyone, and welcome to this weekly session that we conduct, Ask AuxEn Anything. And as you know, that this is an online platform for civil and structural engineers to interact with us and ask their doubts or queries that they may have related to any steel RCC design concept or any project that they are doing or construction site issues. So, this is the 50th such episode that we are conducting, and let us begin with today's questions. So, first, I'll take the questions from the Google form, then, we will move on to the questions from the live audience. Okay, so let us start then. Uh, just wait a minute. I hope my voice is audible. So, this time we don't have any queries in the Google form. So, I'll move on to the email questions. I will move on to the question asked on email. So let me just open uh, email and let me see what are the queries. I hope my voice is audible. So Mr. Raghu has put in a list of queries. He is a practicing working professional from Bengaluru. So he has provided a list of queries. So I'll just copy those and put it over here. Uh, So his first question is, how should a retaining wall with pile foundation be properly modeled and analyzed in analysis software? I have tried several approaches, but I am not obtaining realistic pile reactions. So for this, if you are trying to have a retaining wall on pile foundation, first you should understand how the configuration is going to look like. Blindly just going into model and trying to do something does not help. So first you should look into what type of configuration you are going to come up with. My computer seems to have stuck, so just a minute. I'm not able to see anything. It's a black screen. Just let me see. Yeah, I hope this is visible. My computer just went black a little while ago. Anyway, so I was telling you that understanding what kind of configuration you are going to come up with is quite important when it comes to retaining walls with piles. So let's say this is the fill you want to retain, and here you have come up with some retaining wall, okay, and maybe toe, heel, whatever. Sorry, let us draw like this. So this is the kind of retaining wall you have come up with, okay, and if you are able to have this, I think this is called as heel, and this is called as toe, I guess. So if you are able to have this heel over here, and in spite of having this heel and in spite of, let's say, this load acting downwards, counterbalancing the moment, if you still have overturning, then one of the options can be to, let's say, have some piles over here. So what these piles are going to do, these piles will help you to counteract the uplift. Okay, so these piles will help you to counteract the uplift. So this can be one of the configurations. Now in plan view, it may look like this, that this is your retaining wall in plan view, and you have got the toe portion, you have got the heel portion. Now at certain distances, at some interval, whatever interval you come up with, you can, let's say, provide these type of piles. Okay, So these piles can be distributed along the length of retaining wall at whatever design interval. Oh, is it not visible? My God, what has happened? Just a minute. Is it now visible? So I'll just quickly show you what was the question. How should a retaining wall with pile foundation be properly modeled and analyzed? So I was telling you that one of the possible configurations can be this. I hope now it is visible. So one of the possible configurations can be this, where you have this retaining wall and then there is a fill over here. Now due to large overturnings, let's say you're not able to somehow take care of the uplift, then in that case what you can do, you can add piles over here. These piles will help you to take the uplift by developing tension. In plan view, these piles can be distributed in this manner. So see, one pile, two pile, whatever that you have to decide according to your calculations. Maybe only one pile suffices, like this. Okay, so that pile takes the tension. It helps you to resist the overturning moment. Or maybe you are providing two piles, whatever configuration you come up with. So this can be, let's say, one of the possible options if you want to integrate piles with retaining walls. Now another option can be that instead of providing a continuous base slab, let's say this is your wall in plan view, this is your plan view, this is your heel, or let's say you don't even provide heel. So you have this wall and now you provide pile caps. Okay, so you provide pile caps at regular intervals. So there is no heel toe as such. You are providing pile caps at regular intervals, and then there are piles that you have provided. So from the pile cap, the retaining wall is starting. This can be one of the options available to you. So in sectional view, it will look like this, that this is your wall. I have not provided any toe, heel, or anything like that. So this time I'm trying to take the moments by overturning moments of the retaining fill by this pile cap and piles. So whatever fill is there, it will be resisted by this pile only. Okay. So this can be one of the configurations that you can think of. Other possible configurations can be maybe if the if you are able to provide, let's say here is your fill, and this time let's say because of some configuration you are able to provide a wall over here, but you are not able to access this side. So in that case you can have arrangements like this. In this case, if you are providing piles, the piles will be under compression, right? Because the overturning moment is like this and it will create compression in the piles. So you can think of this type of an alternative also. There can be another alternative where you deliberately, just to counterbalance this movement, you deliberately do what? You provide piles after some distance like this. So providing like this, what it will do? So the axial load over here, okay, axial load over here, the self weight of the wall, this will create a resisting moment to the overturning moment of the fill. And piles you can slightly displace from this distance, from this face. You can have the pile slightly away, so that the sulfate of the wall will create an overturning balancing moment to this overturning moment due to soil. So this arrangement can also be thought of. So whatever arrangement you are coming up with, it will depend on your uh, site conditions and the choice that you are making as a designer. Okay. Right. Then his next query is rough foundation design. Many engineers calculate the modulus of subgrade reaction by this. If this approach is adopted, does it not effectively yield a value corresponding to gross SBC? Is this method technically correct and acceptable? during analysis. See, technically your subgrade modulus should be given by your geotechnical report. The report should give you the subgrade modulus, because please understand that soil is a not a perfect spring and not a linear spring. So just by doing k upon x, sorry, let's say just doing dividing SBC by x to get the k value or subgrade modulus value is not a very appropriate way of doing it, because here we are assuming that the soil is behaving as a linear spring, and therefore we divide the bearing capacity by the settlement and get the k. So I would say this is not a very appropriate way of doing it, because here we have assumed that soil is behaving like a linear spring. So technically the geotechnical person, after doing the testing and on the basis of c phi etc., they should be giving you the k value. But if you don't have any other means, let's say, then you can take this k by doing this. Any k that you take to begin with, anyway you have to do what, you have to then see the bearing pressure and the settlement again. That means, let's say you got some k, you found out some k by assuming some bearing capacity and some settlement. Okay, then you found out this k, this k1, let's call it as k1, this k1 you used in your software, say for stat foundation or whatever, and then you analyzed your uh, foundation system again. Then you see what is the bearing pressure that you are getting. I'll not write SBC over here, let's write bearing pressure that you have assumed. So again, you will see what bearing pressure you are getting, what settlement you are getting. Then you will have to cross check whether that bearing pressure that you are getting is similar to the bearing pressure that you had assumed while calculating the K. Also, you have to see the settlement value that you are now getting, whether it is matching with the or similar to the settlement value that you had assumed while calculating this K. If not, then you again, let's say, calculate K2. So this time the K2 will be your bearing pressure upon X2, let's say. Then again this K2 value you will use. Once again you will do your analysis. Now you may get some bearing pressure 3 and settlement value something like this. Again you will see whether this is similar to the value that you had assumed for calculating K. If not, again change. So this sort of iteration you have to keep on doing until you get the similar bearing pressure and similar settlement value that you had assumed while inputting the K value. So why I'm telling you all this is that it does not matter with which K value you start with. Understand? Whether you are taking SBC upon settlement, or you are taking 2.5 times SBC upon settlement, or you are taking 1.5 times SBC upon settlement, it will not matter. Why? Because finally you have to keep on doing these iterations till the bearing pressure and settlement value that you had assumed uh, for calculating the K value matches with your actual analysis output of bearing pressure and settlement. So this iteration has to keep on happening. So what will happen, whatever your starting point may be, we are saying that until the convergence is achieved between the assumed value of bearing pressure and settlement, you have to keep on iterating. So maybe if you assume, let's say someone assumes SBC upon settlement and gets a K value, uses it. Someone else is using 2.5 times SBC upon settlement and using that K value. So these two people may have to do different number of iterations. But finally, you should be trying for getting the same bearing pressure value and settlement value that you had assumed while calculating and inputting the K. Did you get it? So this thing also happens with the geotechnical engineers. Ideally, what we should do is that once, let's say, you are analyzing any foundation system, whatever raft, whatever, and then let's say your geotechnical consultant has given some K value, you take that K value, analyze your foundation system, find out the bearing pressure and settlement, and go back to your geotechnical consultant and tell them that this is the bearing pressure and settlement you are getting. The consultant will then give you a newer K value. So this iteration they also do. Okay. So that's why it does not really matter with which k you are starting, because you have to do the iterations until convergence is achieved. Okay. Then he is asking what is the reason. However, the resulting base pressure were observed to be identical in both cases. What is the reason for obtaining the same base pressure? See, you must understand very basic mechanics that k value is nothing but a spring constant. So if you are, let's say, applying some P, okay, and here you have put some K. K is nothing but spring constant of the spring, okay, and let's say you had another footing where the same P value was used, but this time the spring stiffness was something different, K2. So what's going to change if I am applying the same P and if I have the same area, base pressure, base area, what's going to change? Is P by A going to change in these two cases? Hello? Will P by A change? Mr. Suraj Nair is asking factor of 2.5 required in K value. That's what I explained for the last 10 minutes. So just go back in the video and see what I tried to explain. Okay. So Py is not going to change. That means whatever your spring stiffness you may have assigned, whether it is K1 or K2, your base pressure is not going to change. Understood? What's going to change? Your settlement values will change. So here you might get some delta 1 settlement, here you might get some delta 2 settlement. So quite obviously, if you have, let's say, an isolated foundation condition, whatever K value you put, your base pressure does not change. Okay, only your settlement value changes. When does the base pressure gets affected? See, your base pressure may get affected in cases of combined foundations or raft like situations. There is a possibility that your base pressure gets affected. Why? Because now this is an indeterminate system, and if I put spring stiffnesses over here, now because this is an indeterminate system, the spring stiffness may affect your settlement, and that settlement may cause some changes in base pressures. So when it is a case of isolated foundation, there will be no change whatever K you put. But if it's a case of raft or uh, combined foundations, there is a possibility that base pressures may show some differences when your spring stiffness K changes. Why? Because quite obviously now this is an indeterminate system and settlements may lead to changes in pressures. So that is the reason why in many cases, even after changing K, you don't see a lot of difference in the uh, base pressures in your situation. Okay, do you understand? Yeah, in case of raft, I just tried to explain that there is a possibility that if there are large settlements, and that too will happen when your column loads are quite non-uniform. Okay, so if this was, let's say, 1000 kilonewtons and 200 and 100, now there is a large non-uniform settlements in your raft. So because of that non-uniform settlement, there is a possibility that your pressures may be slightly altered. What will alter more is the moments. So if you were to check your moments in your raft, okay, more so than the base pressure, what is going to alter might be your moments in your rafts because of these unequal settlements or non-uniform settlements. Okay, you understood? So in this raft-like situation, base pressure may show some variations because of the non-uniform settlements that you might get due to different K values, but more the more affected value would be the moments and shears in the raft. And in the isolated footing, you will see no change. It will be almost similar. Whatever K value you put, it will only be the settlement that changes. Okay, then his next query is, in several geotechnical reports, a total settlement value of 125 mm is specified for raft foundations. I have never seen any report which is giving 125. I don't think 125 mm settlement is appropriate. You should see uh, how come that report is giving you 125 mm. You should ask the geotechnical consultant why 125 mm settlement is being given. because in my opinion it's quite a lot. Yeah. So this point you should try and discuss. I have generally seen 50 mm, 75 mm, or 40 mm settlements being given in your raft. So generally we try to stick to, let's say, around 40 or 50 settlement. Then he is asking, in case of individual piles with pile caps interconnected by tie beams, can the foundation system be treated as a pile group for purpose of settlement analysis? In such a scenario, is it acceptable to assume a settlement of 75 for the calculation of pile spring stiffness? As per the relevant Indian standard, settlement limits are specified for single piles with no explicit provisions for pile group settlement in such configurations. No, I am not sure for pile groups. For pile group, what is the settlement value? I'm not sure what the code says. Uh, Generally, as you are saying, around 12 is what we take it. Mr. Ajinkya is saying IS 16700 allows 125 settlement. Yeah, that's fine. That's for tall structures, very tall structures, unconnected, with basements, etc. Maybe they are allowing 125, but generally it's a pretty high value, right? For tall structures, 50 stories, 30 stories, maybe because you are not able to manage. I guess they are allowing 125 settlements. Yeah, I think so. They allow 125, but that's a lot of settlement, and especially if you have podiums, interconnected basements. 125 settlement will be in your main building portion, but your podiums and uh, let's say the unconnected basements will not have a settlement of 125. Then it will become a real problem in managing such high settlements. So I'm not sure about pile caps. What settlement value the code permits, I will also have to check. Uh, because as you are rightly saying that around 12 is what is considered for finding out the uh, working load of the pile. So how can we have 75 I have no answer right now on this point, last point. Okay. Right, so these were his questions by Mr. Raghu. We don't have. Okay, Mr. Ilakkaya Rajan is saying he is from Chennai, working professional. He is asking how to deal with basement wall expansion joints if building is 100 meters long. So why do we want to provide expansion joints? Don't provide expansion joints. See, we always get confused that if building is more than 60 meter, you have to provide expansion joint. It's not necessary. You don't provide expansion joints. You design for the temperature stresses, provide adequate shrinkage reinforcement. So you will be fine. No need to provide base expansion joint. So he's saying in a sectional elevation, let's say this is 100 meters, and suppose he has two basements. So obviously in basements, no one will recommend you to provide expansion joints. Okay. So I would say don't provide expansion joint anywhere. You may try to find out the temperature related reinforcements, and then accordingly provide reinforcements for it. Okay. Just hold on. Is that understood? So this rule that basement, if you have more than 100 meters, you have to provide expansion joint. It's not necessary. You may take that call, and in such cases, let's say if water pressure is quite high or there is a significant water table, no need to provide expansion joints. Design for whatever temperature effects are there, and provide that additional temperature reinforcement in your slabs. Just give me a minute. Yeah. So my suggestion is don't provide expansion joints. Instead, design for the long length and design for the temperature related reinforcements that you may require. So that is how you should try to deal with it. Shrinkage strips, no, shrinkage strips, it is risky in basement slabs if you are providing, and let's say you have water table, if you are providing pore strips or or shrinkage strips, it is also not a suggested scenario for basements where you are going to have, let's say, possibility of water coming in. Even shrinkage strips is not a good way. Then next query is from engineer Karthikeyan. He is a working professional independent consultant from Chennai, and he is asking, please tell us about how rod bracings work in PEB buildings. As usually, I have seen only hot rolled sections for bracing. In one of the projects, they have used only rod for bracing in roofs and walls with portal bracing. How the rod bracing works? No, see, bracing basically works when you are, if this is your portal system, how does bracing work? So bracing uh, resists the lateral load in through axial forces, through generation of axial forces. So now what these pre-engineered building manufacturers do these days, that to achieve less weight, let's say, they will give these bracings, assume that they are only effective in tension. Okay, so the bracings, they will assume that they are only effective in tension, and if that is the case, they are allowed to provide very slender bracings. That means they will provide, let's say, a bracing with having a slenderness ratio of only, let's say, 350. So the L by R they will maintain at 350 around, and that's how they provide this kind of a tension bracing rod. So generally, what 80 dia. So some people only even provide only a bar, 12 dia bar, or something like that. So that even does not have a slenderness ratio of 350 sometimes. What you see in the PEV structures, they will only provide a bar, but then that bar is pre-tension. You must understand. If they provide that bar, it is usually pre-tensioned bar. Yeah. So it's not sagging, it's a pre-tension tight bar that they provide, and that they even do not follow the L by R 350 requirement. So they will pre-tension it, and that is what they say, that it will be resisting the lateral loads. However, in my opinion, these types of bars that they provide, rod bracings, they don't even pre-tension it, so it's a risky proposition, because what will happen, there is a sag because of the self weight. Now what will happen when lateral load comes? First, a lot of the lateral load will be sort of spent in tightening or straightening of the bar and to remove its sag, isn't it? So what that means is that your portal will undergo some lateral deflection until this bar just tries to straighten. So there will be those levels of deformations that your portal will have to take. So these rod type bracings are not a good way. We don't allow it on our projects. Instead, what we do is that we ask the PEB supplier to provide hollow sections, pipes as bracings. So there they will ensure L by R 350, a slenderness ratio 350, and then they provide hollow pipes. Generally, you will see 80 dia pipe or a 100 dia pipe being provided, pipe bracings. So these rod bracings are quite, I would say, inappropriate, because if you are providing rod bracing, they should be properly pre-tensioned, but nobody does it, so it's a risky proposition. Okay, so this was his query by engineer Karthikeyan, and these were the queries on the Google form. So now let us see the queries that have been put in the live comments. So first comment is from engineer Sumit Shah. He is asking difference between plastic design and LRFD design. See, plastic design means that we, let's say you apply a moment and you, sorry, you apply a load, UDL, let's say, and you get a moment in a simply supported beam as WL square by 8 maybe. In a fixed end, you apply some and you get some moments. Okay. Now in plastic analysis, what we do is we say that our section does not fail, or our cross section does not fail when it reaches its maximum yield levels. So we'll say that our section will not fail when it reaches its yield level. Okay, whatever FC. Okay, let's say this is compressive stresses, these are tensile stresses. So the section is not failing when my materials reach their yield levels. No, I'll say I can keep on increasing the loads on this cross section till this all the fibers reach their yield level. So what will happen at yielding? Let's say if this was to reach their yield levels, what will happen beyond that? If I increase the load, more fibers will undergo yielding. Yeah, because if once it reaches yield, if I try to increase the strains, the stresses don't increase, but only the strains keep on sorry, the stresses don't increase, only the strains keep on increasing. So more and more fibers will undergo yielding, and then a state will come when all the fibers in the cross section have reached their yield level. So this is what we call that our section is now acting as a hinge, because it offers no resistance to any rotation. So in plastic analysis, what we do is we say that our structure can take the load up to the point where hinges are formed, and those hinges don't lead to any collapse mechanism. So we will allow the hinges to form as long as there is no collapse in our structure. And then at that instant, whatever are the moments, we will design our cross section for it. So whatever are moments and shears, we will design our cross section accordingly for it. So this is what we call as the plastic analysis, that instead of just stopping at the elastic level, we will say that our structure can take more loads till plastic hinges are formed, and till the time a collapse mechanism is prevented, we can have more loads, and then we design our section for that level of moments and shears. So this is called as plastic analysis. Now what is next question you have asked? What is the LRFD? See, LRFD is a design approach. So see, you can have a plastic analysis. Okay, let's put it this way. In LRFD, what we are doing in LRFD, we are saying, so it's a completely different thing from plastic analysis. Plastic analysis is an analysis technique just to analyze our frame and see what level of loads it is able to resist. So plastic analysis is more of an analysis technique just to see what level of loads it can resist. Now, in LRFD, what we are saying, it's a load and resistance, load and what they do call it, load resistance factor design, maybe something like that. So here what we are saying, that whatever are our actions generated due to external loads, they have to be less than the nominal strength. Okay, so I'll say that whatever are the actions generated from analysis, they have to be less than the nominal strength of the cross section. So now in strength, we reduce it by this strength reduction factor, or let's say we call it as the partial safety factor for material, and we increase these analysis forces by partial safety factor for load combinations. So this here we will multiply it, let's say, let me just omega, some omega. So this value will be partial safety factor for loads. So this will value will be typically more than 1, and this will be the reduction factor for materials. This will be less than 1. So finally our aim is to provide the strength in the section which is more than the actions. So now these actions can be derived using elastic analysis or your plastic analysis also. These actions can be derived. Okay. Now, generally in our codes, all the analysis techniques we use, we limit ourselves to elastic analysis only. We don't do plastic analysis anywhere. And then we may follow the LRFD technique or ASD or whatever. Okay. All right. Then Mr. Ajinkya is asking if we design a beam for torsion, ETAS shows torsion reinforcement separately apart from shear reinforcement. Please show how to provide the torsion. See, you must understand that when you design your beam cross section, the torsion reinforcement that you get, talking only the transverse reinforcement right now. So the torsion reinforcement that you get, and let's have this discussion with respect to Indian codes right now. In American codes, the treatment is slightly different. So whatever torsion reinforcement you get from your ETABS output, it is only for these two outer legs. So only two outer legs contribute to torsion. Okay. Now when you are being given the shear reinforcement, in shear reinforcement, whatever legs you have provided, let's say in case of my beam, I had provided three-legged stirrups. So there was an outer ring and then there was an inner link like this. So to resist the torsion, only the two outer legs will be effective. So you will say that only legs 1 and 2 are going to resist torsion. To resist shear, all the three legs can be considered to be effective. So 1, 2, 3 to resist shear. Okay. So basically I am trying to tell you that let's say you get your shear reinforcement as some 400 mm square, let's say, per meter, and the torsional reinforcement you are getting some 600 mm square per meter. First of all, you see in the Indian code, I don't think they give a separate torsion reinforcement. That is given only in case of ACI. That is only given in case of ACI. Please understand. Only ACI gives you additional torsion reinforcement separately. In the Indian standard, the treatment is that we combine the shear and torsion, and then there is that formula given in the in the IS code. The treatment is different. In the IS code, there is a combined formula given from where we get the reinforcements for shear and torsion both. So that formula says that for two-legged stirrups, this is what you need to provide. Okay. So if ETABS is giving you, you need to first see which code you are using. And if I were to just show you that formula for combined effects of torsion and shear, it says, yeah, this is the formula. So if you see that this is the formula, two-legged, and here they are quite specific, two-legged closed hoops. Yeah. So now in this there is a torsion also and there is a shear also. So for both combined, you find these two-legged stirrups. Okay. So whatever you are getting, this is for the combined two-legged stirrups. Now out of this, let's say you also have this formula for shear reinforcement 0.87 Fy. How does the formula look like? No, Vu is 0.87 Fy. Oh, sorry, that is Vs. What is the formula? 0.87 Fy ASV or AV, let's call it AV D upon S, I think. Yeah. SV. So from here, I may get the shear reinforcement requirement as VU or VS into SV upon 0.87 Fy D, right? So this is the shear reinforcement required for corresponding to the VS, okay? And now this is the two-legged reinforcement required for combined action of torsion and shear. So accordingly, you can then judge that how many or what reinforcement has to be there in the two-legged and how much of reinforcement has to be there for the, let's say, the middle legs if you want to provide. So this type of calculation you have to do. This is what happens in the IS code. In the American code, they clearly give two separate values. They give you the AT upon S. In the American code I'm talking about, where AT is the torsional reinforcement only for the outer leg, and then you have the value of AV upon S, which is the total shear reinforcement for all legs combined. So your total transverse reinforcement becomes, because this AT is the cross sectional area of one leg only, so your total transverse reinforcement requirement becomes something like this. So in the American code, it's a direct way of adding it up. In the Indian code, uh, it's not so straightforward. You have to do something like this. Mr. Ajinkya is saying, so we do not need to provide torsion reinforcement separately. See, you first cross check whether ETABS is giving you as per this or not. So I think it should give you as per this. If this is what is being given, and let's say you are happy with providing two-legged reinforcements only, then go with this. Okay, then go ahead with this. You understood? But let's say if your reinforcement requirement that you're getting from here is a lot, then the strategy that I'm telling you to adopt is that for shear, this is how or this is what you require. Now these can be multiple legged reinforcements also. And for combined torsion and shear, this is what you require, but this has to be a two-legged reinforcement. Okay. So then you will have to find out that if I'm providing some internal legs, how much area I can provide to internal legs and what has to be there for the two outer legs which are to resist torsion and shear both. Right. Okay. So this was Mr. Ajinkya with his query. Then we have next question from Mr. Manish Kumawat. If bars are not provided with proper cover in lift and they get pushed on one side, what is the meaning of pushing? What are the consequences and how to reduce its effect? See, cover is not related to strength in any manner. Cover is there for durability. So I don't know what is meaning of bars getting pushed. So if you have not provided adequate cover, it will affect your long-term durability and serviceability of structure. Okay. Mr. Magaj is asking how to convert axle wheel load of vehicle into kilonewton per meter square. Uh, Maybe you will need to follow some IRC documentation, but I think you take the axle load divided by the contact area of your wheel. I think generally the contact area is taken as 15 centimeters square. I think so. So accordingly, you need to, or you can convert the wheel load into kilonewton per meter square. Then Mr. Tariq Ahmad is asking, how can partial stiffness be calculated in ETABS when designing column jacketing, when some longitudinal bars terminate at beam level only and few bars continue through the slab? See, I will say that stiffness will not be so much affected by your reinforcements. Okay. So reinforcements, I don't know. First of all, the stiffness you want to calculate is for the column or for the beam column junction at, I mean, at what location you want to calculate the stiffness. I'm not very sure with your question. But understand that reinforcements do not contribute a lot to the stiffness overall. So it's going to be It's going to be the cross sectional area that is going to affect your stiffness more than reinforcements. Okay. Now, if it comes to, let's say, a beam column joint, and then you want to provide the, or then you want to calculate the stiffness, then that's a different issue. Then it will depend on how many reinforcements at what location, what and which reinforcement is going inside the beam, and accordingly, then you might have to come up with some technique to calculate the stiffness. But if it's only the stiffness of column, or let's say if it's a stiffness of only the beam, uh, the reinforcement bars will not affect your stiffness calculations as such. Okay, because the moment of inertia added by the bar will be negligible. Mr. Raghu is asking for a 10-meter high retaining wall supported on 750 dia piles at 2.25 meter spacing with a 6.5 meter base. How should this system be modeled? No, no. How have you come up with all these spacings first? How have you come up with all these values? First, you need to see whether what should be the pile spacing, what should be the uh, what is the pile load, how much load it can resist, what is the overturning moment on your retaining wall. So first, you need to see all those things. How have you decided all these values beforehand? First, you should come up with your configuration that you want to provide. So he's saying that this is his retaining wall, 10-meter high, and 750 dia pile. So now 750 dia pile, where and how it is getting supported, whether you are providing a base slab like this, or you are just providing pile caps at certain intervals. So all those decisions you have to first take. Modeling will come at the end. You should not start with modeling. Modeling will be the end. Will be the end step. First, you need to see what system you are going to adopt. So as I was telling you, if this is the plan view, you might come up with the system where you have these pile caps retaining. This is the plan I'm showing you on the right side, and this is the fill over here. And let's say you have come up with pile caps like this, and from the pile cap, your wall starts. Let's say at the end of pile cap, you provide some beam like element from which the wall starts, right? So then you have to first come up with these distances. What should be these distances? That will be decided according to the overturning moments that you are getting and final pile reactions that you are having. So for modeling, you may model this as a line element. Okay, model your pile cap as a line element, provide pile points, provide pile spring stiffnesses, or if you wish, you may provide this as a shell element, provide these points, provide spring stiffnesses. From there, you have this retaining wall, model it as shell, apply the loads. So these types of things you will have to first do and then decide your configuration. Yeah. So Mr. Karthikeyan is asking, can non-structural walls be modeled in ETABS? To see if it is non-structural, why do you want to model it? Why do you want to design? Why do you want to analyze it or include it in an analysis? If it's a non-structural wall, don't model it. Just take the loads, and that's it. So if you are providing a shear wall, sorry, if you are providing a lift RCC wall, if it's an RCC wall connected with your slabs, etc., then it is going to provide, or it is going to provide you stiffness resistance. So then it has to be taken in your model. But let's say if you are not providing a lift core in RCC, and let's say you're going to have a brick wall around your lift, then you need not model your wall because it's a brick wall. So that decision you have to take. Yes. Anything else? So I think these were the queries this time that were asked. So we have taken up all the queries from the Google form and the email and uh, live comments. So I guess that's it for this session. You can continue to put your queries. Mr. Ajinkya is providing some input between two piles. There should be a tie beam which will support the wall, and that beam needs to be designed for torsion. Now, why does it need to be designed for torsion? You don't need to design the beam for torsion. This beam, orange beam, if you are providing, oh, you are saying the twisting due to the overturning. That's what you are saying. No, no, no. But this understand that your pile is like a spring-like element. Okay, so this having before this orange beam has torsion, this entire system will uh, settle due to the pile settlement. So there won't be much torsion that you would see in these orange beam. If it was like a fixed support thing instead of piles, then you might have seen torsion. But understand that because your pile itself is a uh, is not having very large stiffnesses, your pile will settle down. So there won't be much torsion that you will see in that orange beam. Anyway, okay. So I think that's all for this session then. Uh, we have taken up all the queries. So you can continue to provide your queries in the Google form. Once every week when we meet, we take up your queries. So the link for Google form remains the same throughout the week. You can keep putting queries. And if you want to connect with us on WhatsApp, then this is the link through which you can easily connect with us on WhatsApp also. So let me just put that WhatsApp link. Yeah, so this is the link to connect with us on WhatsApp. I've just put it in the comments and here it is. Right. Mr. Manish Kumar is saying if we provide reinforcement in rectangular form, if the bars are out of one side as compared to its original position, then we bend to align. Is it correct? Yeah, ideally the bar should not be out of position, but if they have become out of position, you can always joggle them in a slope as your SP16 recommends, in a slope not steeper than 1:6, and then you can joggle your bars and then continue and try to maintain its new position. Okay, all right. So I think that's it for this session then. Thank you very much. See you next week with uh, another episode of this weekly interaction that we have. Thanks for joining and bye bye.